In the quiet hours before dawn, a new chapter in AI research emerges around the idea of conditional memory for transformers. DeepSeek unveils Engram, a memory module designed to store and retrieve knowledge efficiently. Unlike the popular MoE route, Engram aims to decouple memory from computation, letting both work in harmony. At the core, Engram reimagines engrams as learnable, hash-based vector lookups. The retrieval phase compresses local context and maps it with multi-head hashing for near-constant time lookup. During fusion, a gating mechanism weighs static memory against dynamic hidden states. Imagine a student in a hall of encyclopedias who can pull facts instantaneously. Engram sits inside the transformer backbone, parallel to a mixture of experts' layers. The system handles local dependencies with precision, freeing attention for long-range reasoning. A 1,000 billion parameter engram shows memory can reside in accessible, cost-effective CPU memory. The materialization of sparsity allocation reveals a U-shaped performance curve. Best performance emerges when Engram roughly takes 20 to 25% of the sparse budget. With 75 to 80% allocated to MoE, the model reaches peak capability. A 270 billion parameter Engram 27B model demonstrates strong gains across knowledge tasks. In knowledge benchmarks, Engram 27B outperforms baselines on MMLU and CMMLU. Remarkably, Engram also boosts general reasoning on BBH and ARC challenge. Code generation and math solving tasks also see notable improvements. To understand why, researchers analyze effective depth, where memory reshapes computation. Logit Lens and CKA tools reveal that Engram increases usable depth without adding layers. Engram activates strongly on fixed phrases and proper nouns, injecting static representations directly. In long texts, Engram handles local dependencies, letting attention focus on long-range links. This enables better performance in contract analysis, literature comprehension, and large code bases. Engram's engineering leverages deterministic hashing to enable prefetching before calculation begins. This design allows storing massive memory in CPU DRAM instead of GPU memory. A practical benefit: lower hardware cost with only minor latency increase during inference. Engram fits into the broader DeepSeek v4 vision, combining memory with modular computation. MoE provides dynamic reasoning while Engram handles fixed knowledge, together forming a brain-like system. In this system, memory retrievability is guaranteed by deterministic lookups, not learned search. The researchers demonstrate a scalable pathway to trillions of parameters without exploding memory usage. Infrastructure-aware design enables memory tables to live in CPU RAM, with GPU fetches kept lean. This work builds on earlier DeepSeek milestones, moving from MoE-based sparsity to memory-enabled sparsity. In summary, Engram is like a bookshelf in the brain of a transformer, enabling quick lookups of facts. The future architecture may weave MHC constraints with Engram as a hippocampus-like module. What this means for AI: faster, smarter reasoning without bloating compute cost. As research continues, the field watches closely as Engram challenges how we think about memory in AI. This video will summarize the essence of Engram and its potential impact on large language models. Thank you for watching this exploration of conditional memory and transformers. End of video. A new axis of sparsity has emerged, inviting engineers to rethink AI memory. If you enjoyed, you can dive deeper into the Engram paper and related DeepSeek research. Credits roll with visuals of data streams and memory vectors circulating like a cybernetic bloodstream. Final thought: memory is not just storage, it is a doorway to smarter, more efficient AI. This 3-minute journey has traced how Engram transforms the way transformers access knowledge. From retrieval to fusion, from static memory to adaptive intelligence, the future's here. We'll continue to watch as researchers push the boundaries of scalable AI memory. This is the Engram era in AI, where memory and computation learn to cooperate.